Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off last week, where we had drawn the equivalent circuit of a single phase induction motor. So in this lecture I will continue with this same circuit but introduce a few more concepts which are very particular to a single phase induction motor, or for that matter any induction motor. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses that you can access through my own website, that is pythonpowerelectronics.com. So once you do come to this website, you will see this button Learn, and that takes you to the course page. So I'm going to click on it and it takes me to the course listing page. So these are the list of courses which I have currently. Right. The very first course, which is called Simulating Power Electronic Circuits Using Python, talks about how you can simulate power electronic circuits using Python and Python Power Electronics. And it is available on the MOOC website Udemy. The next course is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python packages, and specifically the SciPy package and the signal package within the SciPy package to design and analyze filters specifically for power engineering applications. So I have a special case study where I design a low pass filter and a notch filter with a power engineering example in mind. The third course is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can model magnetic components like inductors, coupled inductors and transformers using Python and Python Power Electronics. The fourth course is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python packages such as the Python control package to analyze and design controllers, and in this case specifically for power electronic applications, taking a single phase grid connected converter as an example. The very last course I have is a free course which is more of a motivation course. It's called Why Specialize in Power Electronics, and in this I talk about the main challenges and opportunities in power electronics, and it is mainly targeted towards junior undergraduate students or even high school students who are looking towards which domain they should specialize in. So the link for this page is available in the description of this video. If you are interested, please do check it out. So coming back to our equivalent circuit. So this is where we had left off in the previous lecture, and just a quick recap, the reason why we came up with this is from our basic definition. That is, we saw that our induction motor is of this construction, and which means it has a stator and it has a rotor that is a squirrel cage rotor, which means it consists of bars that are short circuited on both ends. The stator will have, of course, an AC coil, right? Because this is a single phase induction motor, which means we are going to apply a single phase voltage to the stator, and therefore there will be an AC coil in the stator. And this is the diagram. You see, the main winding, we won't talk about the auxiliary winding right now. It has the main winding, which is the winding in the stator, and there is the squirrel cage rotor. So the way it works is, we have for that reason said that this is the source voltage, and there will be of course a certain winding resistance of the stator coil, and sometimes we also say that some of the other losses can also be represented by the stator winding resistance. But typically this is just the stator winding resistance, right? Now, we have said that the actual winding has this inductance L1, right? So for example, we can say that it is an inductance Ls, but this total self-inductance, all of it will not, all the current that flows through the coil will not result in a flux that links with the rotor. So for example, the flux which is produced by the stator coil, all of it will not appear in the air gap so that it can be linked with the rotor. Some of it will escape. This is called leakage flux. That is the flux which is produced but doesn't do anything useful, right? Some amount of leakage is always there in any system, not just electrical systems, but every system, right? So therefore, we need to account for this, and this leakage inductance is that particular inductance that accounts for the leakage flux. Once we have the leakage flux, after that the remaining inductance is the magnetizing inductance. This is the actual inductance that results in the flux which is produced in the air gap. And this flux which is produced in the air gap is what actually produces the useful work which is It induces an EMF in the rotor and produces torque. In addition, we had also connected this resistance across it because this resistance represents the magnetic losses in the system. So which means it represents the eddy current losses and the hysteresis losses, because once you have a magnetic field, you will also have these losses, right? There will always be losses in any magnetic material, and this resistance RC represents that. Once we have all this, the result is we have an induced EMF at the end of it, right? This induced EMF is basically represented as ES. This is simple because this is Faraday's law. We are applying an AC voltage across the stator coil. Therefore, the current that flows through the stator coil will be an AC current, and the flux that is produced is also going to be an AC flux, which means it is a changing flux. Therefore, by Faraday's law, whenever a changing flux is linked with a coil, there will be an induced EMF, and this induced EMF is directly proportional to the rate of change of flux linkages. Right? So this is what this induced EMF is. And as we have already seen, since the flux that is produced by this stator and is in the air gap, okay, we are neglecting this is excluding the flux which is leaking, the flux produced in the air gap, that links with the rotor as well. And therefore, since we have a flux which is changing and is linked with the rotor, there will also be an induced EMF in the rotor, and that's given by ER. And since we have a rotor which is consisting of bars short circuited on both ends, the result is there will now be a current flowing in the rotor, and this is the rotor circuit. It has some resistance, it has some inductance LR, and it has some resistance RR. So this is where we had left off. So now let's go back to we were using this, we just googled this web page, right, and we had gotten this link. So the question is, we were here, this is where we are, and this is how I had resulted in this. For example, this is where we are. Now, as you can see, this is very similar to a transformer. Very similar to a transformer. The only difference between a transformer and an induction motor is, in a transformer, typically there is no air gap because you don't need one, right? The main idea of a transformer is to transfer energy from one winding to another with the minimum amount of loss. So there is no point in having an air gap. In a motor, such as an induction motor, an air gap is absolutely essential, because without that you can't have a rotor which is rotating within a stator, right? That's not possible. So therefore, there's going to be this air gap. Besides the air gap, there is one more little detail that we need to take care of. Now, an induction motor will be rotating at some speed, right? The main concept, or rather fundamental property of an induction motor is it will never rotate at the same speed as the synchronous speed of the flux. What that means is this. Let us now talk about one concept, and that is we talk about the concept of NS, right? So actually, let me go over to my Excel sheet. It's better to write these things, and let me create a new sheet. Ended up creating two sheets. Let me delete this. So we just need this, and I'll just use it for my formula. This is not actually an Excel sheet, this is a formula sheet. So what we say is we are applying a voltage, right? So we are applying, just write AC voltage. We are applying an AC voltage of some frequency F, and this frequency F is in Hertz. Because of this frequency F, this results in, you can say, a flux which is rotating. Now, for now, let us consider a very simple induction motor which has only two poles, right? So which means you can have a multi-pole induction motor, but for now, let's say the number of poles is equal to 2. Is equal to P is equal to 2. So what this means is that the stator is wound in such a way that there is one north pole, there is one south pole. And we'll talk a little more in detail in the next few lectures when we actually start thinking about flux. But for now, just basics. So you can wind a stator in such a way that there are multiple poles. You can have two north poles, two south poles. You can have 3 north poles, 3 south poles, and so on and so forth. You can have any number of north poles and south poles, and you can wind it. For now, don't think about it. Let's just say we have 1 north pole, 1 south pole, just like a magnet, simple magnet, right? So we have wound our stator as a simple magnet. Now, in such a case, the frequency of the flux, right? This hertz frequency, F, has hertz as a dimension of hertz. And hertz is equal to a dimension of per second. I'll just write this down, as this may not be very clear. Per second. That's what hertz is. So quite obviously, you can write something called omega. And this omega we can represent as in radians per second. Alright? Or rather, we can say that if this is the hertz, right? This is the hertz, the frequency. What will be the omega? The omega corresponding to this is of course 2 into pi into f. This is the angular frequency. Another concept that we need to know is, if we say that this is the frequency f, what is the speed corresponding to this f of the flux, or rather what is the synchronous speed? Now think about this. If I were to express this frequency in per minute, right? So basically I'm just saying, I'm going to say something called ns. This is, you could say, actually it will correct it for some reason, ns. ns is considered as the synchronous speed. And this synchronous speed is defined as the frequency but in revolutions per minute, right? That's the only difference. This is revolutions per second, right? Or cycles per second. Actually, it is cycles per second. Let me write that down. It is cycles per second. And instead, here we have revolutions per minute. So what this means is that if this frequency resulted in a movement, this movement would be in revolutions per minute. So therefore, quite obviously, if I can express ns in terms of f, and this is a simple actually, it will always keep correcting it. This correction is very simple. Just think very clearly. Cycles per second, which means it is f divided by 1 by 60. Right? Just think about this. Cycles per second. If you want to convert second to minute, you're going to divide by 1 by 60, which means this is 60f. Now, later on, we'll talk about another concept, which is number of poles. And when that happens, this becomes 120f by p. But for now, don't think about it. Right? We have a simple magnet, 1 north pole, 1 south pole. So what this means is, if I have this frequency f in hertz, which is cycles per second, that will result theoretically in a synchronous speed corresponding to that, which is in revolutions per minute. And let me write that down. RPM. Actually, I can just, this is conveniently written as RPM. Because when we measure the speed of a motor, we usually measure it in revolutions per minute. Right? That's more or less the convention, especially if you have more or less anything like a tachometer. It will give you the readings in revolutions per minute by default. So, this ns is the synchronous speed. But there's something about an induction motor. An induction motor works in the principle, let me go over to the diagram. It works in the principle that there is an air gap in the rotation in this air gap, or rather there is a magnetic flux in the air gap. This magnetic flux in the air gap produces an induced EMF in the rotor because of the simple reason that it is Faraday's law. When a changing flux is associated with any conductor, an induced EMF flows in it. Now, as per Lenz's law, this induced EMF will oppose the cause that produces it. Right? The cause that produces it is the changing flux. Okay, this is just basic physics, high school physics. Faraday's law states that when a changing flux is associated with a conductor, an induced EMF is produced in the conductor. And it also states that this induced EMF is directly proportional to the flux linkages of this coil or conductor. Lenz's law states that the induced EMF is such that it opposes the cause that produces it. And the cause that produces it is the changing flux. So what this means is the induced EMF will produce a current, and that current will produce a flux, which will be such that it opposes this changing flux. So now think about this. The only way it can oppose this changing flux is by rotating at a speed. Right? Now, if it rotates at the same speed at which the flux is changing or rotating, the result is your induction will be zero, because now this rotor and the stator are at the same speed. And if the rotor and the stator flux, if the rotor and the stator flux are at the same speed, the result is there will be no induced EMF. So therefore, usually the induction motor will always run at a speed slightly less than the synchronous speed. Alright, now I would suggest try to read some of these documents because they talk a lot about it, and that's what this concept is. It results in something called as a slip speed. Slip speed is the difference between the actual rotor speed and the synchronous speed which we just defined. And that's how this is given. This is known as a slip speed. So what this means is that the induced EMF in the rotor and the currents flowing in the rotor, they are not at the same frequency as the frequency in the stator. That frequency in the rotor is the difference between the rotor speed and the synchronous speed, right? Because this is it's like a frame of reference. If you are looking at the frame of reference of the stator, of the flux rather, then in that case, the rotor is moving slightly slower than the stator flux, and this flux and the difference is the slip speed. It is this frequency which eventually is induced in the rotor, right? So we have written in this equivalent circuit, we have written just ER, but in reality this is not ER, but rather it is S into ER. That is the slip multiplied by ER. And similarly, this SLR is also equal to S into LR. So we are taking into account the fact that this induced EMF is at a frequency that is much lower than the stator flux. And number two, because of this difference between the stator flux, or rather the frequency of the stator flux, or the synchronous speed and the rotor speed, the result is the induced EMF is going to have a much smaller magnitude, besides even having a lower frequency, a much smaller magnitude as opposed to the stator. Now, again, I'm going to stop here because the lecture is getting pretty long. The idea was to introduce this concept. I'm just going to save this for now. Is going to introduce this concept of the synchronous speed. We will talk about this again in the next lecture, where I'm going to elaborate about how not only does this entire rotor circuit have a lower frequency, but even the magnitude of this rotor induced EMF is much lower than what would be expected. It is multiplied by the slip S. So for now, I'm going to end this lecture. In the next lecture, we will continue with more details. There'll be a few more lectures of theory before I can start simulating, because I do need some basis on which I can actually start writing some equations. So if you have any doubts, please do post either in the comments of this video, or message me on social media, or send me an email, whichever is your preference. Otherwise, I will see you next week where we will continue with this concept. Thank you so much for watching. Goodbye for now.